Hello and welcome to this video on the production of methanol by yeast. As you should recognize, yeast is essential to making alcohol in just about every fermented beverage. The desired product is ethanol. This is the good alcohol. By contrast, the last thing you want is methanol. This is a bad alcohol. How you can get one and not the other is an important part of any fermentation. The weird thing is that how you actually get the methanol is, to a certain extent, not as well understood, at least not the chemistry. Procedurally, it's better understood, in that we know certain actions will lead to certain outcomes, and these are something we can describe in a great deal of detail with relative clarity. The more technical chemistry isn't so clear, and so, for the purposes of this video, we'll say it now. We're going to go through the major highlight points, but we won't go into the great detail of exactly how it is that yeast chemically makes the methanol, as that's less important for this video. Now, how do you get ethanol but methanol? And this is one of the key points in any fermentation. A pure fermentation for ethanol, such as moonshine, or vodka for that matter, will make practically no methanol. And that's because there should be none of the requisite components or reactants for the methanol pathways or reactions to produce it. Methanol requires a more complex media, like fruit juice or, better yet, a whole fruit to make. Yeast will make methanol from pectin. Without pectin, the amount of methanol that it produces drops off significantly. That is because methanol can also be made from DNA, RNA, and proteins. The amount of these is much less than pectin, and is why it will always produce lower amounts if you do not have a source of pectin in your fermentation. To be clear about it, at the amounts that are generated from DNA, RNA, and protein, it is practically negligible. Practically being a key word there. There are circumstances under which you will still get methanol being produced, and in more significant amounts, and we'll describe those shortly. But first, methanol can be released from methylated pectin by pectin methyl esterases. Generally, this occurs in the plants of their own accord, but when you have the plant matter, such as fruit, in the fermenter with yeast, well, you can see where this might happen. In fact, specifically, the yeast used, especially if it's in a high sugar environment, will start to produce ethanol. But at the same time, it will also push sugars into the anaerobic respiration pathway. So at the very start of your fermentation, even though there is oxygen available, and it will be using that to do the respiratory pathway, it will simultaneously take advantage of the anaerobic or lack of oxygen pathway to use up as much of that sugar as it possibly can. This is a phenomenon known as the Crabtree effect. One of the enzymes that are involved in that process is the pectin methyl esterase. This will convert the pectin into methanol and the pectin sugars that can be broken down and used. Unfortunately, this is also one reason why you will produce methanol to some extent. Fortunately, again, not at very high levels. So you have either simply the hydrolysis of pectin releasing methanol, or you have the pectin methyl esterase. If there is a shortage of pectin, you will obviously get less. But these two pathways are not just important as they cover the normal pathways that lead to methanol. That, of course, being normal pathways. The question becomes, what about the abnormalities that must therefore exist if there are normalities? Abnormal pathways are simultaneously more and less obvious. They're also more and less complex. The first to bring up is heat. As yeast are exposed to levels of heat excessive to the conditions they are adapted to, a yeast starts to lose protein. This protein loss leads to methanol production. Remembering how we mentioned earlier that proteins and particularly amino acids can be fed into producing methanol, this is one way to do it. And this is where those smaller quantities of methanol can become a problem. It's not much initially, as the yeast undergoing the normal process of its lifetime, division, and death will eventually lead to some protein escaping, but not much. If you're stressing the yeast, that number goes up, and it isn't much initially, but enough to cause an unpleasant drinking experience and one hell of a hangover the next day. A part of the stress process that leads to this is an increase in translation, that is taking DNA and turning it into protein. The increased translation does two things. First, it will replace the lost proteins due to the stress of the heat, an important development since there is an amount being lost through that heat stress. The other is the RNA and DNA contributing more nucleotides. The RNA is part of the protein translation process, and these nucleotides will also add to the production of methanol. It's important to us to point out that it takes a more considerable amount of heat than you might think initially, and as a general rule of thumb, if you were talking about an ale yeast that is more tolerant of high heat, something above 30 degrees will begin to contribute to methanol production. But that's a general rule, not a hard rule, just keep that in mind. At the same time, an ale yeast has a much lower threshold. Now we need to move on to the other possibility, or at least a more obvious and more difficult to counteract factor, and that is osmosis, or more accurately, osmotic stress on your yeast. This is the stress from osmotic pressure leading to changes and in some cases an increase in production of protein, or protein translation to be clear again. This translation again is to make up for the loss of proteins due to the damage from the osmotic stress. Much like the translation from heat stress, this contributes to methanol production. So long as your yeast is able to tolerate the environment it is in, for example if you're using a more everyday yeast, such as baker's yeast, it's likely to produce unwanted alcohols and likely a small amount of methanol. For a regular fermentation, or if you're trying to use a lager yeast, or worse yet an ale yeast to produce a high concentration alcoholic beverage, for example if you want a pure ethanol distillate, you're likely to cause a certain amount of stress to that yeast, and it is a good idea to increase the fraction that you separate out from the start of your distillation if you're going to do that. It's simply down to the fact that you have caused the yeast more stress during the fermentation, and it will have likely produced more methanol as a result. These are the broad mechanisms of yeast in making methanol and some of the conditions under which it will increasingly make it, and further, how some of these obvious stresses can contribute to the production of methanol. It's on you then to address how you would resolve these yourselves. Some of them are much more direct and simple. Ensure that a fermentation is conducted at the right temperature. On the other side of that equation though is osmotic stress, which is much harder to deal with, and why, generally speaking, a specialized yeast is used when doing so, because it can deal with the environmental stress that you've put it under when trying to create something like an ethanol wash. Thank you for watching this video. If you found it interesting, consider liking, sharing, and subscribing. Please do post any comments, questions, or suggestions you have below.